According to NASA, the interior of the command module must be protected from the extremes of the environment that will be encountered during a mission. These include the heat of boost, up to 1200 degrees Fahrenheit, the cold of space, and the heat of the directed rays of the sun, about 280 degrees below zero on the side facing away from the sun, and 280 degrees above zero on the other side, and, most critical, the intense temperature of entry, about 5000 degrees Fahrenheit. The insulation between the inner and outer shells, plus temperature control provided by the Environmental Control Subsystem, protects the crew and sensitive equipment during the CM's long journey in space. There seems to be more conflicting information regarding the heat outside of the CM facing the sun. As per the above quote, NASA indicated it was up to 280 degrees Celsius, while other sources mentioned 200 degrees Celsius. But clearly, NASA is indicating that the Apollo astronauts needed to be protected from the extreme heat of the sun. NASA contradicts itself yet again. As we discussed in Chapter 3, Apollo 13 had a rupture in one of the oxygen tanks in the SM. As a result, the astronauts had to power down the CSM. This forced the astronauts to move into the LM while coasting back to Earth. However, it is claimed that powering down the CSM caused the temperature to drop within the crew compartment. Aboard Odyssey, the crew too had been discussing their options. Oxygen tank number 2 was gone, its contents vented to space, but the contents of Tank 1 were bleeding away. Jack Swigert was the onboard expert in the CSM systems, but all three knew the basics of physics. When the pressure fell to about 100 pounds per square inch, 689.5 kilopascals, it would be incapable of providing a supply to the fuel cells or to the cabin, and the temperature too was going down. As Swigert powered down the systems in the command module, it was getting colder, down already to 58 degrees Fahrenheit or 14.4 degrees Celsius, and noticeably chilly. Now the question is, if the Apollo 13 CM crew compartment became noticeably colder, what about the heat from the sun's rays that were constantly bombarding the side of the CM and the LM? Are we to believe that since there was no heat being produced by the CM systems after it was powered down, that the heat from within the crew compartment was now radiating heat into space faster than the buildup of heat from the sun's rays? Heat from the sun that was bombarding the spacecraft hull to temperatures of about 280 degrees Celsius or more? And what about the power systems of the LM? They would have been powered up, so wouldn't they have produced sufficient heat to at least counter some of the heat lost from the CM? If the heat from within the CM was radiating at faster rates than the heat from the sun, then there wouldn't have been a need for the PTC, or at least it should have been slowed down in order to utilize the sun's rays to warm the CM, since according to NASA, there was a concern over the CM systems getting too cold. Incredibly though, we are told that Apollo 13 continued with its PTC even when faced with cold temperatures. And even if the PTC was slowed or stopped periodically, that raises yet another issue. Given that the CM was now vital to the astronaut survival, and that would have remained docked to the CM for most of the mission back to Earth. The fact that the LM structure had even less protection for the astronauts than that of the CM, the LM walls having the thickness of 3 layers of kitchen foil, PTC, according to NASA, would have been a reasonable method for the LM. But now, this would have been counterproductive for the CM, since the CM and LM were docked for most part of the Apollo 13 mission. Thus for Apollo 13, PTC works for one spacecraft, but not for the other spacecraft docked to it. Therefore, once again, NASA contradicts itself. PTC would not have worked. As has been discussed so far, the CM and LM had nowhere near the protection necessary for any one of the 6 elements that could have been encountered in cislunar space. And, in fact, PTC would not have been a solution to the problem of evening out the heat from the sun around the hull of the CM and the LM either. Ironically, that barbecue mode we mentioned earlier, rotating the unprotected craft, actually would have ensured that the Apollo astronauts were like chickens on a spit, cooked, fried, baked, radiated, call it what you will, on all sides. The crew would have been better protected from the solar radiation by not rotating the CSM and using an appropriate shield on the sunward side of the craft. Therefore, since the PTC is not an effective way of evening out heat around the spacecraft, then the ARS and TCS would not have functioned as they were designed to. One system has to complement the other, or the whole system fails. As for the equivalent of 3 layers of kitchen foil surrounding the LM and whatever protection NASA claimed it offered, would have led to disaster by any of the astronauts accidentally putting his foot through one of the side panels. NASA reveals it knew little about the space environment. During testing, it was discovered that extreme temperatures could have damaged the heat shield, making a safe re-entry into Earth's atmosphere impossible. This was discussed during the Apollo 13 mission after one of the oxygen tanks ruptured. There were other considerations too. Jettisoning the service module would expose the base of the command module to an untested environment. Although the heat shield embraced the entire exterior of the conical structure, the main defense against frictional heating on re-entry was a convex base. To expose that to the extreme temperatures of space would be unwise and risky. Moreover, no one knew the effect of jettisoning the service module would have had on the command module. Better to be close to home when that event was necessary, just before entering the atmosphere. From the quote, we learn of NASA's concern about exposing the command module to an untested environment. However, this untested environment was supposed to have been determined during the testing phase of the CM's heat shield in NASA's vacuum chamber, which is supposed to have been able to simulate most conditions of space. But if NASA was really so concerned about this untested environment, then it shouldn't have sent any manned mission without first testing an unmanned Apollo mission beyond low Earth orbit to circumnavigate the Moon. NASA claims to have completed 9 successful manned missions beyond LEO, 6 of which landed on the lunar surface, while admitting their knowledge of cislunar space was limited. Micrometeoroid shielding. This chapter has already revealed the inadequate shielding provided for many of the elements in the space environment for the Apollo astronauts, which was also including the provisions of shielding for micrometeoroids, and as been established, the LM had far less protection than that of the CM. Further, when looking into the data regarding micrometeoroid shielding, again we find incomplete information and/or missing documents. Given that the space missions, manned or unmanned, were in their known infancy in the 1960s and 1970s, and little or nothing was known about the elements of space environment talked about in this book, NASA further realized that it needed to address the issue of micrometeoroids. A micrometeoroid impact alone would have been disastrous for any of the Apollo missions. With the shielding used in the CM and the LM, there was no redundancy. Any failure of one aspect of the Apollo spacecraft shielding would have meant an abrupt end for any mission. NASA launched a series of satellites called the Pegasus missions to collect data on the thermal effects on coating surfaces, radiation effects on instruments, and micrometeoroid impacts. There are no long-term solutions to the effects of the thermal environment coating applied to spacecraft hulls, as has been established in Chapter 4. NASA didn't have the equipment necessary to detect radiation intensities beyond a certain level, therefore further eroding the mylar coating on the spacecraft hull. We'll now concentrate on the Pegasus mission's main purpose, which was to collect data on micrometeoroid impacts. The Pegasus missions. NASA launched 3 satellites in the Pegasus missions program on the Saturn I rocket, along with a boilerplate CSM, non-functioning CSM. The boilerplate Apollo spacecraft were used in numerous tests on the ground as well as in LEO. Of the boilerplate CSMs launched to LEO, 3 of them were used for the Pegasus satellites, which were located in the empty service module. The first Pegasus satellite was launched with Apollo 9, SA-9 on February 16, 1965, while the second was launched with Apollo 8, SA-8 on May 25, 1965, and the third was launched with Apollo 10, SA-10 on July 30, 1965. Note: Apollo 9 SA-9 was launched first due to a delay with Apollo 8 SA-8. These missions are not to be confused with the later manned missions of Apollos 8, 9, and 10. In Earth orbit, the Pegasus satellites extended its folded arrays, which reached approximately 95 feet in length. The arrays were designed for detecting and collecting data on micrometeoroid impacts, and there were additional sample protective shields that were mounted on the arrays. These sample protective shields were designed to be retrieved from a manned mission for further detailed analysis. The design and data from these sample protective shields were to be incorporated into the shielding of the Apollo missions. The whole point of the Pegasus missions was to gain data in support of the Apollo moon missions. However, the Pegasus missions went no higher than 500 miles in orbit, which meant that they were nowhere near the area of cislunar space in which the Apollo missions would have spent the bulk of their time. Data from within 500 miles in Earth orbit would have not sufficed for missions planning a 480,000-mile round trip. That's an area of cislunar space covering millions of square miles. Moving the goalposts. The sample protective shields installed in the Pegasus arrays were to be retrieved by one of the manned Gemini missions, but were not for some reasons ever explained. Although data from sensors was obviously stored, vital information from any retrieval of these panels was lost. NASA worked on a probability basis, which is the norm in a lot of industries, for example aircraft manufacturers. But by the 1960s, aircraft manufacturers had decades of research and data to use as a probability factor. However, at the time of the Apollo Moon program, NASA had at best several years of research and data for its manned space program. So, the probability factor for manned space missions is an unfamiliar environment with such little research and data becomes more of an educated guess at best. The original failure criterion for the SPS propellant tanks was perforation of the SM honeycomb skin panels. Because the failure criterion was too stringent to meet the desired probability of mission success, engineers considered an alternative. If the original criterion had remained, the test shown in Figure 4 would have been an SPS tank failure. This quote is an indication of the strategy NASA used. If the criterion was too stringent for the mission success, then NASA changed the criterion, hence moving the goalposts. This is a strategy prevalent with much of the technology used in the Apollo Moon missions, some of which have been shown in this book.